Okay, so this chapter is revisiting an earlier topic of motion, okay, or kinematics. Remember the root word looks like cinema, kinema, meaning motion. But this time we're going to extend chapter 2 motion, where we had a person or a car walking on a road along a straight line. We're going to extend that to rotational motion. So imagine taking this road, there's the road, and instead of having this person, when they walk on the road, after an hour, they're so far down to the right, you don't even see them. Now we're going to take the road and we're going to bend it in a circle. So the person just keeps walking around and around and around. And an hour later, instead of them being 2 miles down the road, you don't see them. They just keep walking around round and around, just like a track. Okay, so the basis for that is, let's say I have a wheel. So this is like a bicycle wheel, and I'm holding the bicycle wheel, and the bicycle wheel is rotating. Okay, so instead of looking at this person and say, well, their coordinate, maybe here's x equals 0, and here's x equal 2 meters, and there's some final position here. Okay, how do we denote the location, okay, or the position of a rotating object, or an object going around in a circle? All right. So what we do is we draw something called a reference line. So this is my reference line, and it moves with the wheel. So this could be a bicycle wheel. All right, imagine a bicycle wheel, and regular XY axis. So instead of talking about the position X of the person down the road, I want to talk about the angular position theta of the wheel. So just like in geometry class, all angles are measured from the x-axis 0 degrees, okay, and they go counterclockwise, okay, positive from the x-axis. That'd be 0 degrees, 90 degrees, 180 degrees, and so on. Okay, so what we do is they say, okay, the angular position of the wheel theta is along some reference line. So imagine I have some line, that's my reference line there, and let's say the wheel starts here. Let's say it starts at that position. Okay. Well, the initial angle is some theta 0. That's my initial position of the wheel. It's the angular position of the wheel. I wait a little while longer, and now the wheel orientation is up here. Okay, the wheel's rotated a little bit counterclockwise. So this is my final angle. That's my final angular position. Okay, so just like the person walks down the road, they have an initial position x initial, final position x final. The wheel can have a final angular orientation or angular position. Okay, now this could also be, instead of a wheel rotating, it can be a person. Okay, so I have a person that starts over here, and later they walk over there. Okay, remember they're going around a lake, around a circular path. Okay, so instead of talking about their position x or their position y, we talk about their angular position. We draw a reference line, and that angle gives us their angular position. Okay, all right, now the angular position is measured in radians. So we have to figure out or recall what is a radian. So I'm going to skip down. I'm going to come back to this, but I'm going to skip down. Okay, now you may have only done radians in trig class. Okay, so since we're going to be using them between now and the end of the semester, I want to make sure we understand what a radian is. Okay, now first thing you can also ask is, well, what is a degree? Okay, everyone understands what a degree is. Okay, what is 1 degree? Well, imagine you have a pizza, okay, and you take 360 equal little slices. Okay, you chop it up, cut it into 360 equal portions. Okay, one of those, okay, each of those, I should say, is 1 degree. Okay, so that makes sense. Take a circle, I go from the center, and I cut it into 360 equal parts, and each of those represents 1 degree. Okay, now what's a radian? That's a little bit trickier. So I'm going to make an example. Let's say I have 3 shoelaces. Okay, I have 2 pairs of shoes. I'm going to take off the shoelaces, so I'm going to use 3 of them for now. They're all equal length, L, and I'm going to lay them on the floor. Okay, so this will be a top view. So I'm going to put one here. There's one there. There's one there. And I'm going to bend this one so that I have what's called a sector. Okay, looks like a piece of pie, okay, or a piece of pizza. Okay, so that's called the sector of a circle. Okay, if you have a whole circle, okay, just call it a circle. Okay, but this is a portion, the sector of a circle. So the radius is L, right? There's my radius. There's my radius. My radius is L, and the arc length, okay, that arc length is also L. So all three of those shoelaces make that sector. Okay, this angle here, okay, that angle theta, that's defined to be 1 radian. Okay, or you can abbreviate a radian as 1 rad. All right. Now, so the definition of a radian, okay, so 1 radian is the angle that subtends an arc length that's equal to the radius. All right. So for example, if I have a little angle like this, or a little sector here, this radius is big, this arc length is very small. Okay. That angle would not be a radian. This one here, you have a radius here. Okay, there's the radius. Okay, that arc length is huge. Okay, so that arc length is not equal to the radius. Okay, up here in this picture, okay, I made my 3 shoelaces so that this arc length L is equal to the radius. So this angle, okay, is 1 radian. So a radian is the angle that subtends an arc length that's equal to the radius. All right. Okay, and if you do this on your calculator, it comes out to be about 57.3 degrees. Okay, we'll see why that is. All right. Okay, so that's my 3 shoelaces. Now I want to ask, okay, how many shoelaces do I need to create half a circle? Okay, so right now I only have that portion of the circle. I want to create half a circle, 180 degrees. So here's the same picture. So I took apart a whole bunch of shoes. So I have my original picture here. Okay, so I have 1 shoelace. Okay, I have my 2nd shoelace. I put my 3rd shoelace, and it doesn't go all the way. Okay, it doesn't go all the way to the bottom. There's a little gap here. Okay, so how many shoelaces do I need? I got 1, I got 2, I got 3, and I need a little more than 3. I have to fill up that gap. Okay, so how many shoelaces do I need? I need pi of them. Okay, so you need pi shoelaces to make 180 degrees. So 180 degrees is pi radians. Okay, and it makes sense that if you go all the way around, so here I drew our coordinate system. All right, so you start at 0, 90, 180, woo, 270, 360, okay, or 0 radians, pi over 2 radians, pi radians, 3 pi over 2, and 2 pi radians. Okay, so here's the same picture. So I have my 1, 2, 3 shoelaces. I have that little gap. So pi shoelaces is, there's my 3 shoelaces, and I need a little bit more. Okay, so that's why your pi radians is the same as 180 degrees. All right. Okay, so actually, if you took that 180 degrees and divide it by pi radians, okay, that's where you get your 57.3 degrees. Okay, but don't worry about that. Okay, now from geometry class, okay, or trig class, definitely in trig class, maybe not geometry class, okay, they showed you how to find that arc length S. And math books like to use the letter S for arc length. Okay, so you have a sector of a circle, okay, and here's the radius. I don't need to draw it here as well, okay, because that leg is the same as that leg, okay. So I have the radius. Oops, don't do that. I have the radius, and I have the arc length, and I have the angle. And I want to be able to find the arc length, all right? Well, easiest way to remember that is if I have a circle, okay, if I have a circle, how do I find the arc length of a circle? Well, remember from algebra class, that's just called the circumference, okay? And everybody remembers the circumference is 2 pi r, okay? Well, r is the radius, and 2 pi, right? That was famous rapper, 2 pi, okay? 2 pi is the angle, okay? So to go all the way around, okay, that's 2 pi radians. So to find the circumference of a circle, it's the angle times the radius. right? And that's what we have for here. So to find the arc length of the sector of that circle, okay, it's in here I wrote it as, instead of angle times radius, I wrote it as radius times angle. Okay, so most times in math books you see it written like that. Okay, so the circumference of the circle is the radius times the angle, which would be 2 pi for the radius. But here we're doing this in general, just for a sector of a circle, like a piece of a pie. So that arc length is the radius times the angle. Okay, so from the picture above, here are my shoelaces, all of length L. Okay, so my radius was length L. Okay, my arc length was length S. All right, so let's say each of these shoelaces was 4 feet. Okay, so here's my shoelace picture: 4 feet, 4 feet, 4 feet. Okay, and I want to find the angle. Okay, so I'm going to use this, solve this for theta. So theta is the arc length over the radius. So I put in my arc length is 4 feet. There's my 4 feet. Radius is 4 feet. And I do this in a calculator. Okay. And the 4's cancel. Okay. And so to get 1, and the word feet cancels. So I'm left with 1. Okay. 1. And then what do I write? I write the word radian for free. Okay. So before I did that, I canceled out the 4. Okay. I canceled out the 4. Whoops. I canceled out the 4's, canceled out the feet. Okay. I'm left with a 1, and there's nothing to the right of the 1, but then I get to write the word radian. So you can see that the radian is a dimensionless unit. Okay. Meaning it doesn't have dimensions of length, speed, or time. Because if you look back here, you have feet divided by feet. The units cancel. There's nothing left. So that word radian has no dimensions. All right. So as another example, let's say you take a ruler, okay, your 12-inch ruler. So you have a foot, okay. So you have your ruler, put it on the ground, okay, lay it on the floor, and you make a circle, okay, and you're going to walk around that circle, okay. Well, what's the arc length of that circle you're going to walk around, okay? Well, that's our expression, okay. The arc length is r theta, okay, and so the radius is a foot. That's your ruler, okay, and go all the way around 360 degrees. So I multiply those out, and that says 360 feet, okay, and that makes no sense because if you do this in your room, you know that when you walk around your ruler in a circle, okay, that's the center, you're not going 360 feet. Okay, so what's wrong with this is I ignored that unit. Actually, it'd be 360 feet degree, okay, which is useless. All right, so from trig class, this expression, whenever this expression is written, okay, and usually whenever you see a theta in an expression, okay, not a sine theta, okay, not a cosine theta, but just a theta all by itself, that theta usually has to be in radians, okay? All right. So remember, we did the picture with the 4-foot shoelaces. The 4's canceled, the feet canceled, and I just had 1, and I wrote the word radian, okay? So the radian is a dimensionless quantity. So going back to this, if I want to find that arc length or the path length, okay, walking around your ruler, S is r theta, okay, I can't use my angles 360 degrees. Okay. Theta has to be in radians. So the radius is my ruler, that's a foot, and my angle to go all the way around is 2 pi radians. So 2 pi times 1 is 2 pi, okay? There's my foot, which is now feet, all right? And now you ask, well, what happens to the radian? Where'd it go, okay? You don't have to write it. Okay, because remember up here, you had feet canceled with feet, and the radian is a dimensionless unit. Feet over feet is no dimensions. Okay, so you don't need to write the word radian because you know that a distance s, right? On your driver's license, it asks you what's your height. Okay, it'll say 5 feet or 4 feet. It doesn't say 4 feet radians. Okay, that doesn't make any sense. So that's what's weird is the radian is a dimensionless unit. Okay, it's right there. But when you write your answer, you don't put the word radian because you know s is a distance, right? And in the calculator, 2 pi is about 6.28 feet, and that makes sense, right? That circle is definitely not 360 feet, but it is about 6.3 feet. Okay, so I want to go back to page 1. Back to page 1, okay? Because we jumped off of that right here, right? Okay, so in chapter 2, x was the position, okay? That's you walking along the road, okay? Or the car, okay? Remember the gremlin that went down the road, okay? X was your position. Delta x was your displacement, right? That's your change in position. So just like we have a angular position of the bug, so maybe the bug here is at 0 degrees, even though it's supposed to be doing this in radians, and maybe later the angular position is 30 degrees, okay? So you can have an angular displacement. So let's say in this picture, I have a bug here, and I'm going to do the left-hand side first. It goes around once. I have one revolution. The bug goes like this. Okay. What is delta x for the bug? Okay, remember delta x is x final minus x initial. Okay. Well, so the bug starts at x equals 0. Okay. So the initial position is x equals 0. Okay. The final position is the same x coordinate. Okay. So the bug ends up where it started. So it's displacement. This is displacement. Delta x is displacement. Okay. Displacement 0. Okay. The angular displacement is 2 pi radians. So I'll squeeze it over here. So delta theta, my angular displacement is 2 pi radians. Okay. Now, in this same picture, I'll use that color. Okay. Let's say the bug goes around twice. So it starts here and goes around once, goes around twice. Okay. Goes around once, goes around twice. Okay. What is my displacement delta x for 2 revolutions? Started here, went around twice, ended up there. Delta x is 0, or you can write 0 meters. Doesn't matter. Okay. 0 times meters is still 0. Okay. My angular displacement delta theta, it went around once, that's 2 pi. Another time, that's another 2 pi. So it's 2 pi plus 2 pi, you get 4 pi. Okay, so that's the big difference between the displacement delta x, okay, and let's say if you're on the road, as you go down the road, your displacement gets bigger and bigger until you can't see the person anymore. Here, if it's going around a circle, your angular displacement just keeps accumulating quantities of 2 pi.